This next chapter is talking about intermolecular forces within liquids and solids. You have to remember from chapter 5, which is the gas law chapter, that gases do not have any intermolecular forces. So that's why it doesn't mention gases, it just mentions liquids and solids. So let's talk a little bit about the difference between intra and intermolecular forces. The intramolecular forces are really what we've been dealing with up to this point. Those are your chemical bonds. So when we were drawing our Lewis structures, we were drawing our chemical bonds, and those are the forces that hold the atoms together. What this chapter is about are the intermolecular forces, the forces between molecules or between ions. And we have about 6 different classifications of different types of intermolecular forces. We can start talking about some here, but we have a whole other slide that we're going to talk about and hopefully utilize. That's what part of our worksheet is going to be on. And so in order to do this properly in understanding these intermolecular forces, or the forces between our molecules, we have to really make sure we understand molecular polarity again, that we're able to draw and see the 3D structure, be able to find where that partial charge is, because that's really the attraction force that's going to hold these molecules together or attracted to each other. And so this page is really an important page to kind of stop at and look at, and it's in your lab. But really what we have here on the left-hand side are the 6 different types of intermolecular forces. And we're going to go through them pretty quickly. But we're talking about the intermolecular forces in the liquid phase. Okay, so we're talking about the liquid phase, not the solid state. And we have our little descriptions. Now, you'll notice the hyphen. The hyphen is talking about that attraction force, that intermolecular force. So when you're reading it, so for example, ion, what it's saying is you have an ion, an intermolecular force that's attracted to another type of ion. So that's what that description, or the way we're writing it, is talking about. On the right-hand side, we have how we're going to be utilizing the different types of intermolecular forces, but not just the different types of intermolecular forces. We're going to be looking at its molecular weight, the structure, and how that influences the boiling point. And we're going to use the boiling point as this gauge of our overall intermolecular force. We'll probably come back to this slide to kind of go through the thought process, but let's go through the 6 different types of intermolecular forces first. So here's our ion. This is the strongest type of intermolecular force, and the reason being is we're talking about Coulombic attraction, or Coulomb's law, but we have full charge. In other words, we have a positive ion that's attracted to a negative ion. And so it's like 2 really strong magnets, in other words. And we can actually see this take place. We can see that when we're talking about melting points, or same idea as a boiling point, you're breaking these intermolecular forces. And we can see with sodium chloride versus magnesium oxide that this melting point, which is breaking those intermolecular forces, increases when you compare sodium chloride to magnesium oxide. Now, why would that be? Well, that's because, whoops, hit the button wrong, of your charge. You know sodium is a positive, chlorine is a minus, but magnesium is a 2 plus and oxide is a 2 minus. And so we can see that greater strength when you have the greater charge differential. And so this ion force is that attraction force between that positive ion intermolecular force to a negative ion. The next one would be an ion dipole interaction, and we have to remember what a dipole is. And so if you go all the way back to that one page, there's this important statement down here that when we're using these descriptions, when it mentions dipole, you're talking about a polar molecule. When you talk about an induced dipole, you're talking about a nonpolar molecule. So we have to make sure we recognize that that's what that's are saying. And so when we're talking about this, we're talking about the attraction force between an ion, so either positive, another cation or anion, with something that's a polar molecule. And we can see this take place really easily with water, because water is one of the most polar molecules. We can see it has the partial negative charge on this side and the partial positive charge on this side. And so we can see this ion dipole attraction take place, because if we had a cation, which is positively charged, all of our negative side of our oxygen can create this intermolecular force of an ion dipole interaction. And this is the reason why a lot of ionic compounds dissolve in water, because this is a relatively strong intermolecular force. And so what can end up happening is once they dissolve, it can end up hydrating it and ends up helping that dissolving take place by increasing entropy, which is a favored state here. We can do the same thing with an anion. We can see the positive side can be attracted to the anion because of the partial negative charge. And this is a fairly strong charge also, or attraction force, I should say, because of the fact that you have an ion that has a full-on charge. It's not a partial charge, it's a full charge being attracted to a dipole.
When a gas phase sodium ion enters water, it becomes surrounded by water molecules, or hydrated. The ion-water connection results from ion dipole forces indicated by a dotted line. It is difficult to determine the number of water molecules around a hydrated ion, but 6 is a good estimate for most cations.
And so you saw there with the video that how when the ion actually enters that water, you can see how it ends up organizing itself and being surrounded by it, hydrating it is what we call it. You can also see this take place with a lot of different metals, and we'll talk about a lot of this. We'll talk about in 1B, the last chapter that we talk about. But it gives us all these different colors, and we're going to talk about how it creates this octahedral space group and how we can look at the d orbitals. But that's all in 1B. We can see this exact same strength occur with an ion dipole force by changing the charge on the cation and also its size. And so what you're seeing here is this is the amount of energy. Whoops. What happened? This is the amount of energy it takes to disrupt this ion dipole interaction. And we have to think about, well, why is magnesium so much greater? Well, it's because it's a positive 2 versus a positive 1 or a positive 1. And so that attraction force, again, is Coulombic attraction, your attraction between a positive and negative. But then we look at sodium and cesium, and you think, well, wait a minute. The charge is the same. Why is cesium so much less than sodium? And again, with Coulombic attraction, the attraction force is equal to kind of like the charge difference of the positive versus the minus all over the distance squared. And so the distance here is larger because of the cesium atom being larger in size. And so therefore, the actual centers are farther away, and therefore this bond actually, or attraction force, I shouldn't say bond, this ion dipole intermolecular force is much weaker, and so that you're very easy to actually break. And we'll talk more about using this and looking at this in Chem 1B. Right now we're just trying to identify these different types of source of intermolecular forces. If you looked at the list, and if you have that page and you're kind of going through it with your notes, we skipped hydrogen bonding because hydrogen bonding is a subset of dipole-dipole. And so the first thing we're going to do is really talk about dipole-dipole interaction, meaning we're looking at a polar molecule being attracted to a polar molecule. And that's what we're trying to do. And when we look at this, and we'll talk a little bit about this in our lab when we get to the lab that we're talking about. This is an example of we could make this HF, we can make this, we can make it whatever, that's HCl, however you want to think about it. But what you're looking for are two polar molecules. Now, they don't have to be the same because they just have to be two polar molecules. If it's a pure substance, kind of like in our lab, then they will have to be the same substance. But it doesn't have to be. If it's a solution or it's a mixture, then obviously it doesn't have to be the same molecule if you're talking about dipole-dipole interaction or intermolecular forces. The only requirement is that you have two polar molecules. And so this polar molecule, you can see our partial charges are obviously attracted from one side to the other. And this is a dipole-dipole interaction, which is a fairly strong interaction.
Hydrogen chloride molecules are polar. When HCl molecules in the gas phase are cooled, the kinetic energy of the molecules can no longer overcome the dipole-dipole forces between them. The opposite ends of the molecules attract each other and coalesce to form a liquid.
And so we can see up here in the top left corner how hydrogen chloride, which is obviously a polar molecule because of chlorine having a higher electronegativity than hydrogen, we can see that having that attraction force between one another, and we can see how it actually lines itself up and creates this liquid, because in the gas phase, remember, there are no intermolecular forces, and as we cool it, we're recreating it, we're slowing it down, and we're allowing the HCl to actually interact, giving us our intermolecular forces that you see here that were formed. Once you have dipole-dipole intermolecular forces, you get that you're talking about the interaction between two polar molecules. You then can also add in hydrogen bonding. Now, hydrogen bonding is not a chemical bond. A lot of times that's misunderstood. Hydrogen bonding is an intermolecular force. Yes, there are similarities in some of the properties to a chemical bond, but it's not considered to be a chemical bond. It's an intermolecular force, and it's a special case of the dipole-dipole interaction. And what I call this is the Knopf rule. So in order to identify whether you have hydrogen bonding or not, the first thing you're going to do is make sure, number one, you have a dipole-dipole interaction. If you have anything else, it can't be hydrogen bonding. The next thing to identify is you're going to look on the molecule. You're going to have some atomic center X chemically bonded to hydrogen that has some sort of intermolecular force to Y, which has a lone pair. It doesn't necessarily have to have this chemical bond. So a lot of times you'll see it in this form here, where that is the first thing you're looking for. After that, X and Y must be equal to Knopf, meaning nitrogen, oxygen, or fluorine.